Signals travel less than the speed of light. So they are completely causal. Which signals can influence which others, which ones? Now, in flat space, the light cone structure is rigid. So every point here has the same light cone. Here, rigidly around X, Y, T, etc. In curved space, again, this is what I said yesterday, that if you go to the vicinity of a point, you can imagine a small light cone there. And all physical signals which are emitted from that point in an infinitesimal neighborhood have to lie within the local line. I have a trajectory like this, it goes somewhere. And if I want to know whether that trajectory is a physical signal, then I have my curved metric. So I know curved space-time geometry is, and therefore I know the trajectory of light rays, vicinity of any point. So I can draw my little local light cone, and I have to make sure that instant part of the trajectory lies within the local light. Okay. By the way, this is an information. Just stop me at any point. If you don't understand, just stop. So yesterday's rules not apply. Just stop me whenever you feel you need clarification. So this is just saying that nothing can travel faster than light. So the local light cone structure determines what are physical signals and what are physical. Yesterday, a black hole spacetime is one in which you have these local light cones which swirl around a complicated way, but the net result is that there is some interior region from which light simply cannot escape and travel inside forever. So a typical example of a black hole is this over here. So this is a black hole which is spherically symmetric, and for dimensions, every circle over here, as we saw yesterday, is actually a sphere, surface of a sphere. But I'm drawing it as a circle. Everything is spherically symmetric, so on the surface of the sphere, the geometry is completely the same. And so the gravitational field is the same on every sphere. What happens to the behavior of light? If I am far away from here, this is a solution, this is a configuration of the space-time geometry. The space-time geometry at large distances is flat. So it's like the previous diagram. And imagine in this space-time over here is pretty much flat. Imagine that you have a sphere, spherical surface. And there are people, torchlights just sitting on every point of the sphere. And they can shine two sets of rays, orthogonally out of the sphere and orthogonally in the sphere. So there are the ones which are outward, they just go on expanding and they go away. Whereas the ones which are inward, of course, converge. Right? And they all the light rays. So that is the behavior in flat space-time. And that is the behavior which you believe, which is exhibited when you are in this region over here. So here you have the out. Remember, this circle is supposed to be a sphere, and this is space-time. So that's confusing. This is a space-time diagram. So you can think of it as two space and one time dimension. And light rays over here go outside, right? Over here, the radial rays, right? So these are radial light rays. They just go this way, and then the radial infall, the torch lights which are shown inside, they just fall. That is okay. That's just what happens in that space-time as well. Now, because of the curvature of space-time, what is happening over here is that the light is not rigid, as you would not get a black. You would just get a usual case where always the outward rays escape. Okay, because imagine that the flat space-time, nothing special is going on. always have outward rays, maybe you have inward rays, but the outward rays always just now over here, however, as you go in, right? So what this means is that if you want to think about it in flat space time for a minute, then you look at a sphere here, right? You shine outward rays, they always go out. You look at a smaller sphere inside, there also if you shine rays, they will go outside. So how small the sphere is, you're always going to shine rays and they're always going to go outside. And at the even the zero here, it's just a point, there's no problem, right? As long as you're sort of in the vicinity, no matter how small, forget the point, but how the spherical the surface is, the outward rays will just escape outside. So in flat space time, no problem. And there is nothing. You cannot have a black hole in flat space time because from every point, the light escapes to the outside. But in this crazy thing, what is happening is that light waves are tipping. Right? So as you go towards smaller and the light won't start tipping like this. It tip inward towards the direction of smaller spheres. And what happens is that over here, as you go in, if you go right inside, then the light cone is completely tipped here. And remember, all signals have to lie within the light cone. So all these signals, none of these come out. Right? They have to all fall inside. And indeed, they fall inside in this metric configuration. This is singularity. This is where the curvature blows up and everything is infinite. The gravitational tidal forces just tear you apart, infinitely strong, and the light just disappears over here, right? All signals fall in over here, and nothing can escape to the outside. So as you're coming from here, you're tipping up to this point, there's always the outward light ray, which somehow manages to escape. But when you just come exactly to this point, the inward light ray, of course, goes in, but the outward light ray neither falls in nor escapes out. So it just kind of hovers over there. And that is the exterior region and the interior region. And remember, each circle over here is actually a sphere. So this is a three-dimensional surface. It's faced by light trajectories, which neither make it all the way out to infinity, nor do inside. And this is called the horizon of the planet. This is a three-dimensional surface with two-dimensional cross sections, and this is called the event horizon of a black hole. And this particular, so it's not enough just to say, oh, interesting space-time geometry. Of course, it is an interesting space-time geometry. Is it a solution to the equations of gravity? Otherwise, it's not. If it's not a solution, then I would not be interested in this, right? So you wanted to be solution to the are there solutions to Einstein's equations, right, which have this sort of structure? If they do, then you would say that Einstein's equations admit solutions which describe black hole geometries. Okay. So again, just a recap. So just as in Newtonian gravity, how will you find the gravitational force? Well, if you give me the matter distribution, I can look at the inverse square law. I can compute the gravitational force anywhere in space. Right. Once you give me the trajectory of these, wherever the matter is. The distribution of matter to the gravitational force. In general relativity, because the idea is that you no longer, it's not actually the gravitational force. Gravity is the curvature of space-time. Have you had any general relativity at all? Yeah. Okay. So everything is in the curvature, right? And therefore, what takes over Newton's equation is something which relates the energy content, the mass energy content, what is called the stress energy, space-time, to the curvature. So on the left-hand side, you have the curvature, and on the right-hand side, you have the energy momentum content locally. So these are equations which you have to solve. And these are extremely complicated equations. So Einstein really had to struggle 10 years between special relativity and general relativity. He had to learn a huge amount of differential geometry. He had to learn new tools from his friend Marcel Grossman, build up slowly. Finally, after a lot of effort, he had these complicated non-linear partial differential equations which are extremely difficult to solve. Einstein himself solved that. He could not, even though he was the author of those equations, he couldn't find any solutions, but his genius was find suitable approximation methods and then explain various things. Right? So bending of light and this and that. I don't know exactly the history of what came first, what came last, but he could exact solutions. He developed approximation methods to extract the physics out of his equations in physically relevant situations. Enough, a mere 6 weeks after Einstein had his equations, right, in more or less final form, the first solution of the Einstein equation was found. And it precisely described that geometry which I told you about in the previous class. It described the geometry of a black hole, right? Not the inside, but the outside. So the light cone, the event horizon was described by the solution. And this solution was found enough by a German artillery soldier who was serving on the Eastern Front in the First World War. And his name was Karl Schwarzschild. And many inspiring people in this whole story. And he's, to me, really the most inspiring of these people. He was an absolutely amazing person. I think he was born in a reasonably well-to-do family, and he was always known for English. And already in his early 20s, he was kind of a increasingly well-known astronomer. And he was an astrophysicist who not only did astrophysical computations, but he was also intimately involved in telescopes. He commissioned gratings. So after Fizeau, he was one of the pioneered the use of diffraction to separate out images of stars which were overlapping in the telescope. There are things named after him in astronomy, after in astrophysics, after Karl Schwarzschild. So already, in his 20s, he was already on his way up. And 1901, probably the age of 28 or so, he was given charge of the observatory at Göttingen. Now, in 1900, year before that, 5 years before special relativity, much before Einstein ever conceived of general relativity, Schwarzschild wrote a paper where he computed the curvature of the universe if the universe was a sphere, three-dimensional sphere of 3 dimensions. I've not seen the paper myself. I should look at it. But he computed this curvature. And you might then wonder what was going on, right? Astrophysicists who suddenly decided to do this computation much before differential geometry. So Schwarzschild in 1900 did much more differential geometry than Einstein did, throughout. Because Einstein had to learn all this stuff from Marcel Grossman. So how did this happen? So very, very mysterious thing. The reason it happened was that around 50 years, one has to go into the mid-1800s, there was this, what people acknowledge to be one of the greatest mathematicians ever, Gauss, who happened to be in Göttingen. That's just happens. In fact, Schwarzschild, before he moved to Göttingen, Vienna, somewhere, or Munich, where he did this stuff. So Gauss in the mid 1800s had developed the mathematics to describe two-dimensional objects and how they curve. So curvatures and differential geometry, we call differential geometry for two dimensions. Gauss had a very gifted Riemann, and Riemann generalized Gauss's work to arbitrary. So he's like the father of whatever differential geometry we use in anything. And Riemann has a very famous address. I think it's called On the Foundation, where he speculates that perhaps space, perhaps there is a physical reason for space being curved. It's already obvious. And these ideas were swirling around, in Germany. People actually were inspired by these ideas and read up and tried to do calculations. And that's how probably Schwarzschild managed to do this, right? Because it was already in place, even though it was way in the future. So in 1901, Schwarzschild goes to Göttingen, and Göttingen is a observatory. So there's the observatory and there's the department. And but never, it's a absolutely amazing time because quantum mechanics is being formulated. I guess a special relativity done in 1905. So those ideas probably were there. And there were people over there. There was David Hilbert, the famous mathematician who you might have heard of. There was Minkowski, of the space-time. He was on Paul Ehrenfest, one of the people who was in quantum mechanics, came, I think, as a summer student. Like visiting something and took some classes on Schwarzschild. Right? So those were amazing times. So anyway, Schwarzschild must have been exposed to a whole lot of things. I'm very sorry, backpack inside. There's some beautiful quotes due to Schwarzschild, which I cannot tell you right now. They're sort of, I forgot. I should have brought it. I'm a bit unwell, so a little bit woozy. So in any case, Schwarzschild, at the age of around 36, he was an astronomer, and he was given the highest accolade, which was to take charge of the observatory in Potsdam. So this is around 1910, when he was 36 years of age. He was very active, right? So these are all very famous astronomers, Vestus Schleifer and Jacobus Capitin. Maybe I'm pronouncing it wrong. This is a picture taken in happier times. Schwarzschild in that white suit over there. Now, 1910, the First World War breaks out. And 40 years of age. So there is no reason why, I mean, he's not going to be drafted. He's so old. But out of a sense of patriotism, he volunteers to fight for Germany. Because of his mathematical ability, he's not sent really to, he's not shooting guns and so on or fighting in the trenches, but he's right close there. Bullets are flying around. So he is basically, his role, so he was appointed a lieutenant, artillery division, and his role was to calculate trajectories of artillery shells. The western France, then to Belgium, and finally on the eastern, Russia. That was a long battle between the Kaiser and the Germans. So there was in 1914 or beginning of 1915, and there were bullets whizzing. There was all this fighting going on, and there must have been communication with Berlin. In 15, he got a package in mint condition. Einstein's theory, the first address, and this had appeared, and so he looked at it, and within 6 weeks, because I guess he knew differential geometry already, right? within 6 weeks, he got the solution, which is the Schwarzschild solution. And he wrote a letter to Einstein. And I don't have the exact words, I'm really sorry. It's a beautiful quote, and where he says, even though I'm near the gunfire and the bullets and so on in the war, as you can see, I still have time to take a walk in the land. Yes. So Einstein was very pleased, and you can see the sort of whole discourse and the way people behave. Einstein, I presented that paper of Schwarzschild. Schwarzschild was in the front, so he presented it on Schwarzschild's behalf, and Schwarzschild got the. Today, somebody would have stolen the idea and published it on it. Now, not only was Schwarzschild in the middle of all this war, right? He also was, so Schwarzschild was an Ashkenazi Jew. And probably because of the limited gene, they are susceptible to a particularly nasty autoimmune. Skin starts eating itself. So Schwarzschild contracted that disease. So he was actually in a war. There were bullets flying around. Plus, he was dying because there was no known cure. And he published not that one paper, but 3 papers. So one was this exterior Schwarzschild solution. The second one was gravitational field, I think, of some distribution of dust. The third one was computing something called the Stark effect in quantum mechanics. Again, I don't know how he did it. So here was a guy who he cracked GR, he did quantum mechanics, he made telescopes, and through all this, he seems to have been completely cheerful. Right? And then in 1915, or he was discharged, and shortly after that, he dies. He was dying already at that time. So, when you complain about exams, a little bit extra coursework, or you don't have time for this and that, or maybe instructor is not, then maybe just remember Schwarzschild and kind of circumstances under which he did his work. Just absolutely amazing. So I really find him inspiring figures in this whole story. Okay. So let's go on. The solution was appropriate to the gravitational field of a point. So this was the exterior gravitational field of something which had collapsed on a point. So if you wanted a more realistic solution describing gravitational collapse, then again, if you wanted to solve the equations, you have to do some simplification. So you assume spherical symmetry. Already, even then the equations are complicated, but you assume spherical symmetry. If you have a spherical shell of matter, which is weight in form of a black hole, that solution was found in 1909 by Oppenheimer and Schneider. But curiously enough, in 1938, there is a mysterious duck, probably, right? So, published in a German journal, I can't pronounce the name. If you look at the title, it just says B duck, Visheshaka, and some British English spelling of Calcutta. And that's it. So he has this paper where he has several solutions. And one of them is what was later known as the Oppenheimer. Later on, much later in the 90s, there was an eminent relativist. So there's this journal, General Relativity and Gravitation, and at least they used this golden oldie where they would take up a paper and analyze it. So somebody analyzed this. It was clear that that did not know exactly what the import of the solution is. So when you solve general relativity equations, you can write down a solution, right? But that's only half the job. You need to be able to know what that geometry corresponds to. So that this geometry actually corresponded to, this beautiful black hole structure, etc. That he did not know. So he just solved some equations, and he had solutions which were known. He had some solutions. And this was what was later on called the open. So in that acknowledgements of that paper by Vishweshwar Dutt, he acknowledges a professor in, I think, Calcutta University. There, it is most likely that he was a student in President's College. And after that, he just disappears from sight. And I was just looking on the net. So this is, I mean, I don't know how reliable this information is, but other people have also mentioned it, that 2 years later, a botched hernia operation, right? So he exists. Now, in 1943, there's another very interesting solution. So this is just dust which is falling and collapsing. There was also a solution to the Einstein equations of spherical symmetry of a star which was radiating. So you model the radiation by what is called null dust, zero mass dust, and when you write down these solutions, around 90% of the job to know what are the correct coordinates to use to model a particular situation. And the person who did this was P.C. Vaidya. He wrote down the solution of a radiating star, but very, very easily you could use one set of coordinates. Instead of radiating from a star, you could also use radiation collapsing and forming like this. So the solution is then known as the Vaidya solution. I don't know who wrote down the black hole solution first, but evidently, I mean, he had done most. So Professor Vaidya is another amazing person, and if there's a very nice documentary on Professor Vaidya. So Vaidya was, he was, I think, born in a small village in Junagadh, somewhere in Gujarat. Very interested in math and science, so he went to Bombay to study math and science. And he finished his probably bachelor's, and then he came back to Gujarat, to Rajkot, there, and he started teaching in that college. Change of management, Varadarajan took over, and there was some disagreement with management, and so Vaidya resigned his job, and it was close, yeah, it was 1940s, early 1940s. It was a time where the whole country was gripped with, the fervor of the free. And Professor Vaidya was an ardent Gandhian, so he really had a lot of regard for Gandhi. Documentary, he says that what he learned from the Gandhian philosophy was to always, given some situation, to try and how he could use that situation to help other people rather than himself. Yes, that in one line, I think, says what his outlook was. So what did Vaidya do at that point when he was not at this Rajkot college? The artist, I've forgotten his name, who started something called the Ahimsak Vyayam Sangh. This was an organization which trained the youth to be satyagrahis, how to go and protest violently and take part in rallies. Now, this was already 1902 or so. And around 1942, Second World War already started. And Hitler went and invaded the Soviet Union. And since this guy who started it was leftist, to him, the greater evil, rather than the British, was the invasion of the Soviet Union by the Germans. And since the British were allied with, there was a conflict. He didn't know quite what to do, and this Ahimsak Vyayam Sangh was dissolved. So again, Vaidya finds himself in 1942 saw what to do. And he's making a living by giving tuitions, and he's barely 23 age. So he decides, he remembers that sometime in 37 or so, that he had attended a lecture in Bombay by V.V. Narlikar. Those of you who know Jayant Narlikar, who passed away recently, V.V. Narlikar was Jayant Narlikar's father, one of the people who brought general relativity. So he remembered this lecture by V.V. Narlikar. Absolutely fine. He remembered being completely fascinated by general relativity. And he just wrote to Narlikar, who was in Banaras, Hindu University at that time. And he said, "Can I come and work with you?" I said, "Sure, you can come and work with me. But in this come and can I not?" There was no monetary issue. So there was no money, and he was not going to be paid. Vaidya was 23, 24, was newly married. He had a 6-month-old daughter. And they just went. They got on a train and they went to Banaras. Vaidya rented a small place to stay and teach. I think he was trying to tutor some Nepali prince over there to make his ends meet. And 3 times a week he would go and meet Narlikar, and then he would try to do some GR, sort of chase up and down in his room and try and think of that. Then in 1943, early 1943, the Quit India movement had already started in 1942. But then there was violence. I think, I don't know my history that well, but I think there's violence from the Indians. They could not sustain the non-violence. And there was even more violence from the British. And with all this killing, Gandhiji he went on a fast. And Vaidya is in Banaras, and so every day in the morning he goes to the Ganga, he has a bath, comes back. 3 times a day he's going to Narlikar. Rest of the time he's in his room trying to make some computations or doing his tuitions. But every day in January he reads the local newspaper because he's very worried. And apparently I think the 10th days are critical. Gandhiji is just hanging by a thread. And Vaidya is very, very worried, very worried. So he's pacing up and down his room, pacing up and down his room. Suddenly the Vaidya. And within a couple of weeks, he dies. So Professor Vaidya is also of the Indian Association for General Relativity. And I would attend these meetings, and Professor Vaidya would be there. In fact, he would feel cold, so he would put on a glove, put his hands. And next to him was Chaudhary, another amazing person, and they would sit together. So I've seen him from afar. I had just come back to India as a young faculty member. I was too scared to go and talk. So the lesson is, please don't be scared. You never know how long people last. Both of them are gone. And I regret that I didn't know all this, and I never, I knew that they were very well-known people, but I never, like this for oldies. Right? I'm an oldie now. But had I known what I knew, I would have really talked to them, not about physics, but also about their lives, which was so interesting and so amazing. So in any case, I think repeated brief of this whole thing is that there are people who are brilliant and passionate, and then these, spite of all sorts of material obstacles, they seem to be able to do what they want. And in fact, in the case of Vaidya, and we'll see again, very often it happens in moments of a lot of tension that some spark happens and you get an idea.
Sir,
Yes.
Professor Vaidya gave the solution for radiating star?
Yes.
Snow dust.
So he modeled radiation as called massless dust. He didn't write the electromagnetic tensor, but he wrote the radiation as what is called massless dust. So the dust which travels on light trajectories, not on time light trajectories. So not massive dust, massless dust. And radiation. But I think somewhere, I don't know who found the collapse solution. but uses basically similar coordinates. So, okay, so now all these solutions which were found, whether it was Oppenheimer, Schneider, or Vaidya, or whoever, all these solutions, because they were exact solutions, spherical symmetry. And all these solutions, basically the takeaway lesson was that a black hole would form through spherical collapse whenever the mass of a distribution was compacted into a size less than called its Schwarzschild radius, which is given by that quantity r equal to 2gm, that is dimensions of length. And so whenever you stuff in that much of that size, then you have a black hole in spherical symmetry. This is fed with gravity. And these solutions all had a horizon at rgm, and there was always a singularity, like that wavy line I drew. So this was all on the mathematical front. I don't know much of astrophysics, but it's interesting that on the astrophysics front, a young 19 years old, 25 years, 19 years, is just amazing. A 19-year-old Chandrasekhar was on his way from India in 1930 to take up a fellowship at Cambridge, and interested in white dwarf stars. And he showed, I think, following work of Fowler, gravitational contraction, that white dwarf stars would sort of collapse. There was a deep, I mean, there's a whole story about it, which I won't get into, but basically, if they had enough mass, then they would collapse under their own weight. So they would no longer be white dwarfs. What they would be, he didn't speculate on. The idea was already there. He had something which was massive enough that he could overcome what is called degenerate pressure and collapse. So similar by Oppenheimer and Volkoff on neutron stars, where they actually said that there should be an indefinite collapse. 1939, Oppenheimer and Volkoff, and a follow-up paper by Oppenheimer and student Schneider talked about. But they were really, unlike that, they were not just solving something, they were really looking for black holes, and they found it. So Oppenheimer had already done spectacular work on black holes. But then 1939 is the year and then all the attention went to fission. And so those of you who've seen the movie, you know the story of Oppenheimer. So after 1939, he doesn't work on black holes at all. It's all about nuclear fission. So it's a strange thing how history plays a role in. Maybe Oppenheimer would have the frontiers of understanding of black holes much more. In the 60s, there was the discovery of these objects. Again, I'm not an called quasars, and they emit huge amounts of energy from a very complex region. People thought that the only thing which could explain them was perhaps a central black hole. But in spite of all this, people felt that, the solutions which had been written down were in exact spherical symmetry. So look like here, there was complete spherical symmetry. But I mean, in a realistic situation, real world, it's never going to be exact spherical symmetry. Right? There'll always be some non-spherical part which is collapsing here and there. There'll be some perturbation. And so people thought that, well, this is an artifact of assuming very high symmetry, because they were very worried about the singularity. Singularity is just where all your physics just breaks down, and they didn't want to accept that there was a singularity. They couldn't break around it, and so they thought, oh, these are just maybe unphysically sort of symmetric solutions, and they're not realized in nature, so we don't need to worry about them. People didn't take these things very seriously, in spite of this, in spite of some astrophysical evidence. So what would one do in this situation? Well, at that point, I think sometime in the 1950s, John Wheeler, who was Feynman's advisor, suddenly got very interested in general relativity. And he has a lot of ideas about quantum gravity and so on and so forth. In fact, when I was a graduate student, in Syracuse. He came to visit once or twice, and he was already in his 80s, and I never knew whether he was senile or whether he was always say random stuff. I mean, to me it sounded random, but apparently that was the way he was. Ideas really ignited a lot of discussion and thought and politics. So in any case, what John Wheeler did was his group tried to do the logical thing. Said, okay, let's try and see if we can solve the Einstein equations and find black hole solutions. Once you leave this spherical symmetry, right, it is impossible. Analytically, you cannot do anything because the equations are just too complicated. So that didn't go. But then suddenly in the 1960s, you have this, I mean, I think after Schwarzschild probably, or after Einstein, maybe, the most amazing guy he comes onto this thing from out of nowhere. He's actually a mathematician. He was taught on geometry or something. And the three, there were a few very sort of, there was Einstein, then there was his research associate who actually used to come in Syracuse, a very gentle, lovely old man. I met him. And then there was Dennis Sciama in England, who was propagating general relativity. He was also a very, very, very nice person. There's Ted Newman in the US, and there was Andrzej Trotman in Poland. So these were the people, and John Wheeler. So these, the whole can, like, what is that number called? There's a mathematician's number where you can trace your lineage to one of these great man. So here, sorry? Well, there's a Gauss, there's an Erdos. There's an Erdos. This way you can trace your lineage to one of these. So Sciama at that time was, Penrose was talking to Sciama a lot, and he got him this. And so, and Penrose just decided to completely tackle this same. So if, in interviews and so on, he says that I would always some other way of thinking about things, right? There's no point thinking about the same problem in the same way as other people. I would attack problems in my own way, which was a different way. So here, what he did was he didn't look at the Einstein equations at all. He didn't try and solve for non-standard equations. Instead of doing that, which was basically impossible, he focused on the peculiar behavior of light trajectories. So the fact that outward rays kind of just at the horizon, they don't neither fall in nor do they go out, converge. His genius was to say, okay, these on the event horizons of black holes, I know that these things happen. His real genius was to take that idea out and say, let me consider that idea on its own. What idea? The idea of what is called traps. Okay. So let's look at this a little. Okay. So, sorry. Now, this is exactly what I said earlier. As I said, if you consider the surface of a sphere in this room, you shine light radially outwards, the spherical light runs increasing, yeah, and the light rays diverge. You shine light inward, and that is a typical behavior. In space-time, this behavior can change. And in particular, it might happen that both the outward, so this is a statement locally. By locally, I mean you go here, you just look very close to the surface, shine light here, right? And you normally outward ones will diverge, right, near the sphere. But it can happen due to the behavior of the light cones that even the outward ones converge. The light cones are tilted in such a way that even the outward converge, right? And that is exactly, for example, inside the event horizon of a black hole. Sorry. Inside the event horizon of a black hole, the are also converging because they're all falling in. You see, this is surface area equal to 0 as you're going inside the surface. So it's totally weird. The outward guys also kind of focus inward. They don't go out. Otherwise, they would just diverge. But this is only a local state, close to the sphere. That's all you're interested. You go here and shine light very close to the sphere. Two light rays close by, and you see, oh, do they diverge? Do they converge? Now, this was so when this happened, the outward rays and the inward rays converge in the vicinity sphere. And by sphere, I mean a topological sphere. I don't mean a round sphere or the fact that there has to be some spherical symmetry. You just need a closed object. It's just some, it can be a deformed sphere, just some bag which is closed. You look at the surface and you shine light outwards, you shine light inwards, and both sets converge, and then you say that you have a tap surface. Now, in the case where this is not that important, but to tell you, when the inward light converges and the outward light is converging nor diverging, so it's collimated, then this is called an outer surface. But I don't think we have time to worry about this in this discussion. Okay, now just a word about trapped surfaces and the event horizon. Trapped surface is what is called a quasi-local structure. A local structure is something which is close to a point. A quasi-local structure, why quasi-local? Because you have a sphere, you have an extended object, but you're still looking in the vicinity of that edge. So light is locally trapped because you're only looking at things in the vicinity of a sphere. There's no statement about how light behaves away from that surface. So away from that surface, it might again, for all you know, it might again start diverging out. We are not saying that. We are saying you just go in a small infinitesimal neighborhood of the surface and you see whether your light. Okay. So the notion of a trapped surface, namely both sets converge, light is locally trapped. What happens to it later on, we don't know. In contrast, an event horizon, if it exists, by definition divides the space interior and an exterior region, and light from the interior is globally trapped. It can never, even under finite time, you wait for however long you want to, the light from the interior will never get it. So, and that is what we mean by that. And the rays will just about come out the event horizon, as we saw, and the existing event horizon means that there is a part of space-time which is hidden from the outside. But to ascertain whether you have an event horizon or not, for infinite time, right, to see if anything comes out or not. So you need the whole space to evolve before you can decide whether there is a hole or not. So it's a very unsatisfactory notion. Right? It's called a teleological notion. It's something where you cannot say now, but it's only after the whole space-time evolves that you can say whether the space-time is a black hole or not. Because you never know, right? You wait for, a billion years, nothing has come out, but maybe, billion one light ray comes out, right? And then you don't have a black hole. So, whereas the trapped surface is just a quasi-local, right? Now, technically, in the literature, in GR, a black hole is said to exist only if there is an event horizon. Whatever is behind the event horizon is called the black hole. And in the spherical collapse black hole solutions, matter collapses to a central singularity. This is important. This singularity is hidden from outside view by an event horizon. Symmetric solutions, there is an event horizon and it hides the singularity. Okay. Now, just to go a little bit ahead, what Penrose showed is that if a trapped surface develops anywhere in space-time, to the future of that trapped surface, there is necessarily a singularity. Okay, I'll repeat that. Penrose shows that if there is a trapped surface anywhere in space-time, then to the future of that trapped surface, there is always going to be singularity. He doesn't yet say anything about hole. So that's why this result of Penrose, this is what fetched him his Nobel Prize, single PRL paper 1965. The paper showed that there was, the existence of singularities, and therefore it's called a singularity theorem. In addition to that, Penrose formulated hypothesis. So that has not been proved. People are accumulating evidence. And the hypothesis is that in realistic collapse, whatever that means, so it's vague so that you keep dodging counterexamples. But in realistic collapse scenarios, any singularity is always hidden behind an equations. Okay, is that clear?
Yeah. Spherical symmetry is not assumed.
Yeah, I'll come back to that. The notion of a trapped surface doesn't assume scenarios. Right? So what Penrose says, if there's a trapped surface, I'll have a singularity which is formed. I still don't know whether that singularity is visible outside or not. So in addition, he has, due to strong intuition, something which he calls censorship hypothesis. That is, in the cosmos, there is a censor who will never allow you to see the singularity. So all singularities, whenever you have a singularity, it will be hidden behind an event horizon, and therefore, for him, if you have a singularity forming in, automatically happen that. But that is not proven. What is that you will have a singularity? You had a question? Okay. So now, yes.
When you say big picture, what does that?
Yeah, I'll tell you. So now we'll come in detail. Yeah.
What is the physical idea of this cosmic censorship conjecture? Like, why would the nature won't let us see what is?
Yeah, so I don't know. I mean, this is Penrose's intuition. And there are counter examples, right? Where, in fact, Pankaj Joshi has been in his group. Pankaj is now at Ahmedabad University. For a long time, he has been churning out exact solutions. But okay, the issue with exact solutions is that they're exact, right? So then you can say, oh, they're too much this, or then they're not generic. There's something about non-generic about them. So, but Pankaj believes that no, I mean, he has accumulated enough evidence. You should admit what are called naked singularities which are not clothed in an event horizon. This is Penrose's intuition, and this is what a large number of talented mathematical general relativists are trying to prove to, with less. Go ahead.
Sir, how would naked singularity look like physically?
So there will be a region of very, very curvature which will be able to send light to you, or say, so you will be able to see something bizarre. Probably you might be able to get quantum gravity.
That allows to see quantum gravity.
Because as I said yesterday, that before this curvature becomes infinite, the curvature will become of the inverse Planck length squared, and effects will come.
Okay. Like if something is trapped.
So if you have if matter collapses, you form a singularity, and if that singularity, that region, that classical region around the singularity can communicate with you through light signals or through whatever, then you will be able to. So you'll be able to see whatever is happening, right?
But it might not be a singularity, right? Because how usually this infinite curvature.
Yes.
And so that means like nothing can escape from there.
Not necessarily. That's the whole point. Singularities can be right. It is just a place where the infinite tidal forces, but it does not mean that nothing can escape there. The statement that nothing can escape from somewhere is an event horizon. It's got nothing to do with singularity.
We can have, okay. And
You can collapse and just something like a big bang. Something collapses, a huge big bang, and something came out. So for example, in the case of past singularity, we are living evidence of the fact that, so if we could look, we can't, but if we could look behind, there's no obstruction to seeing what came out of it. That's why we discussed yesterday that same the argument indirectly. So these are two distinct notions: event horizon and singularity. And Penrose conjoins them and says that all singularities in the obtained by collapse are clothed by horizon, so you don't see. That is
Okay. Will singularity try to like preserve any symmetry, any kind of?
I mean, so no, there is, so let's come to the argument.
Right.
And by the way, when you get tired, just tell me, I'll stop. So I don't have, yesterday, I don't have something which I have to complete or anything like that. Sorry, I can go on.
Because
Yes,
how would the light cone look for the naked singularity then?
yeah, so we can maybe talk about, because for that, it's a bit difficult to tell you because, one notion of what are called Penrose line. That's the best way I can tell you about, so light will escape. I mean, light near the singularity, light will, it's, you, instead of thinking of it as a singularity, think of it as a region of extremely high curve. And things emitted from that region. So that's fine. From that region, your space-time is normal and you have light. And you have, but just exactly at that time, you don't know what is going on. But in the vicinity, and anyway, it's an idealization because quantum gravity is going to come into play and lots of other things.
I'm sorry, but like going back to the I'm still kind of not able to wrap my head around.
Yes.
The diagram you showed,
Yes,
so that if you have space-time is curving, then how the light cones form,
Yes.
they cannot escape from there.
yes,
So now again, if we have a singularity
Yes.
that's forming the curvature,
yes.
the light cones of course are not allowing anything to go out. Then how can something come?
That is only for this thing. Clarity was the, you see what happens over here. We can, I'll just say, come back to it again. So what happens over here? You see this singularity, see the, right? Now, if you just extrapolate this light cone over here, right? This is a light cone. The singularity is coming like this. Is it? It's space light. Right? Because it's coming like this. If I do this, this is a space like direction. So the singularity, the Schwarzschild singularity is set. Okay. But you could also have time like singularity. There is no, tells you you can't have.
The time that singularities can be.
Right, but even space-like singularities can be naked. So it's a more you have to look at what is called double diagram. Right, so this is always the problem. I'll have to tell you about Penrose diagram. Of course, if you're still alive after also. So let me. These are all good questions because this is a danger in India that words are not. It's like even in special relativity, if you try to say words, like when wind does something or when that clock, I mean, it makes no sense whatsoever. You wrap yourself up in words come from our everyday intuition. Right? They paint pictures which are intuitive. Best way is to draw a space-time diagram, for example, in special relativity. Everything is clear. Here, there are these things which Penrose introduced called Penrose diagram. There, everything is much stronger. We can talk about it. But what I'd like to do now is to give you an idea about Penrose's arguments because it's a fun thing to do. It's what got him the Nobel Prize, and it's a beautiful structure. So let's slowly go through Penrose's. And if you're too tired, you can go ahead. But let's try and at least do Penrose's arguments. Okay, now the first is that the notion of a trapped surface has nothing to do with spherical symmetry. I mean, I never invoked any spherical. I just said you take any topologically closed surface with the topology of a sphere. I shine light out, I shine light in. In the neighborhood of that surface, the light converges, and I have a trap surface. Nowhere have I mentioned that the geometry should be spherically symmetric. Okay. So this is, so what Penrose just separated the idea from spherical symmetry, but then free of spherical symmetry. It's just that surfaces. So trap surfaces are, you could say, are much easier to form, you would think, than something which is exactly spherically symmetric. It's too rigid. Physical things. Trap surfaces could form without form. So that is the idea. Now, let's of this. So what are the? I will not look at the third part. Third part is a bit technical and complicated. The first two parts, I think, hopefully I can transfer. And I want to transfer. So just for the next 5-7 minutes, somehow try to. I know it's a long day. It's the end of the day, but try to come awake just for have some superhuman concentration for. Okay. So there are two main ingredients. The first ingredient is what somebody asks me about. What is the future? I think you asked me that. So it's structure of the boundary of the future of a two-dimensional closed surface. Surface in space, and it's closed. And I'm going to talk about the structure of the boundary future. I will define the future. The second ingredient is the focusing of light rays matter, and that is what happens in general relativity, and it is the statement that gravity is have. Whenever you have positive energy matter, light focuses. And then the third one we want. But what I'll try to tell you is that already with 1 and 2, you get something extremely exotic, and it has to be easy like this. Okay, so let's go. So consider closed space-like two-dimensional surface. What surface? The future of the surface is that you shoot possible signals from the surface, light-like or I mean, you can, whether they're particles or whether they are light rays, anything less than the local speed. You shoot those signals, and remember, we are in space-time. So it's a bit, you have to think a little bit differently, because if I say light is going like this, you only see light going in space, right? But you have to remember that time is ticking along. Okay, so actually in a space-time diagram where time is going up, light is going like this, it actually means time is also going on to the future. So what is the future of surface? It's very simple. It is all points which are reachable by signals which travel at the speed of light. Okay, not the speed of, you don't send light signals, you send all possible particles. Okay. Shoot down the particles here, there. Then you see in space-time, so particle starts over here. 5 seconds later, it reaches somewhere, then the space-time 5 seconds and whatever space coordinates are. So you have to remember it's in. Okay. So you look at, that is the definition of future, which is quite reasonable. Okay. So if there's a closed surface, you can shoot things inwards also. Signals inwards, outwards, but all the points you can connect in space-time constitute the future of the surface. Okay. Now, if you look at the boundary of that future, then remember that things which are not at the speed of light can be almost sense at the speed of light. So the boundary of this future, reasonably, you can show it rigorously, but the boundary of this future has to be ruled by light rays. Is that reasonable? Right. So if you look at the light of the light, it's all time like, particle trajectories, and the boundary surface of the light, where light goes. So this is typical because you can use as wherever you want, but if you look topologically at the boundary of this future is ruled by light rays. All right. Fair enough? Is that good? Now, because it's not necessary in curved space. I already said even in flat space, if you have the sphere and we shoot things in light rays inside, they all intersect. So light rays intersect, right? They do intersect after some time. So wherever light rays intersect, those points are called cross. Just a name. Two light rays intersect. Okay. Now, just using topology, you can show the following result. Okay, which I am not going to show because even I cannot show it right now. I would have to look at a textbook and derive it for you. But no equations are being used. That is the main. It's not used any abstract equation. He has taken a closed surface, and now I'm looking boundary of the future of that closed surface, and this boundary is the trajectory of light rays which are emanating from that surface. These light rays can cross, and the result is the following, that it can be shown whenever two light, so here again I can't draw a sphere or a three-dimensional, so I'm just drawing a circle, okay, and time is going up like this. So if I look at two light rays, right, and supposing the geometry is such that cross, okay, either in flat space time or curved space time or whatever, they cross. So that point is called a cross. Okay, and that if I connect, supposing I take one of these, any one of these light rays, right, light rays just cross. It doesn't mean that anything bad is happening. One light ray crosses another, and right? I mean, if you look at the example of this of flat space, right? I shine light here, that light will just continue. In the future, it will just exit this way. There's no big deal. Light rays cross all the time. But if you have light rays which cross, and you take any one of them, and you follow its trajectory, all right, and you look at any point to the future of that trajectory, then there is a result which says that point can be reached from that surface by a signal which travels less than the speed of light. Okay. Is that clear? I will repeat it. So here, two light rays, they cross at the point P. Now one of them I am going to extend, and this is the surface. So if I look at any point to the future of P, the statement is that there is always a signal which goes smaller than the velocity of light, which is that. Is that clear? You can reach it by light, but you can also reach it by something else. Just having less than the velocity, provided that that point is to the future thing of two light rays. All right.
The signal started at the same time.
So the signal, so yeah, so what is time? So that's where it gets, so I'm not even saying, I'm just saying that you have a spherical surface which is space-like. That already tells you. So remember, if you're talking, supposing I'm talking about a football or the surface of a football, right? Now, if I look at the football, I'm really talking about the football at a particular time. Because I will not get a spherical surface. I'll get a spherical surface cross time, which will be a three-dimensional object. I'm not saying that. I'm saying look at the spherical surface, which automatically means it at an instant of time. Whatever that means so you can say because you have a global time and all that, but you don't need to articulate all that. You need not have a global matter. As long as you have what is called a space-like surface, the result is true that you you shine light rays outwards, and if they cross, then to the future of that, along the light trajectory, there will always be a particle-like trajectory which meets that. So that is a theorem which only uses topology. Okay. Now, yeah. So
That other particle, which is light,
yes,
that should be on the surface, but not at the same, like, I mean, I'm trying to understand the
Yeah.
image.
yeah,
So it's going to be on the other side.
it will be at some.
Okay.
So it's just the theorem only says that there is a surface from which you will send a light, from which you will send a particle signal, and you will be able to reach that. So where exactly that point is, I will not commit. Right? I mean, I would very much that those can be any of these original points, but I'm, in GR, I don't want to say anything which I don't know. But yes, likely and intuitively, it is from one of these. And again, these statements, I'm kind of exaggerating them to make them comprehensible. This is the qualitative understanding of what is there. The actual quantitative thing is more subtle, and it has to do with infinitesimal things and things like that, so I want to, but I just want broad geometrical picture. It is more subtle than this, because then you look at some sort of differential geometry, things called expansion, something on the tangent space, but basically this. So what does that mean? Now, we already said that the future surface is all points which can be reached by particle signals, right? So this point, any point on that trajectory beyond P, particle signals. So therefore, those points cannot lie on the boundary of the future. The boundary of the future can only be reached by light trajectories, not by if you reach by particle trajectory, automatically here, that is in the future, not in the boundary. Is that okay? No, not okay? Yes. So what did I? Let us look at the future of a closed surface, closed space-like surface, closed two-dimensional space-like surface. What was the future? You shoot signals less than the velocity of light, and you look at all the points you can reach. That is the future. You look at the boundary of that. The boundary of that, the result, whatever is the boundary, it will always be, that's a theorem which I am not plausible, that the boundary of that set, the future set, is always ruled by light rays. That is kind of a. So now what has happened, as I've told you, when two light rays cross, right, and you go ahead, right? Remember, the converse is not true. It is not, we are not saying that every point which is reachable by a light ray lies on the boundary. We are saying that the boundary of the future is ruled by light. We are not saying that you shine light and wherever light goes, that point will automatically not be a boundary, which is exactly why this genius idea of looking at only non-light trajectories are. That is how you do it. It is called the chronological future of the surface. So you look at this chronological future, which is signals which go less than the velocity of light. You look at the boundary of that, whatever are the bound points, you can prove that they are reachable by light rays traveling from the surface. There may be points where you reach by light rays, but which are not on the boundary, and indeed, these points of this type are light rays. If you go ahead to the future of P, you can reach those points by particle trajectories. But the moment you reach them by particle trajectories, you are not on the boundary of the future. You are inside the future. Is that clear? Okay, great. So what does that mean? That means that whenever two light rays on the boundary of the future intersect, they both leave the boundary. Right? They cannot be on the boundary, because then whatever points are to their future are connected by these other trajectories. So whenever these two light rays start off on the boundary, they intersect, then that is the kind of end point. Okay, so keep that in mind. Now, up to now, we have not used any equations, right? We have just said there is a closed surface, this is the future of the closed surface, this is the boundary, this is the characteristic of the boundary, everything is topology. There is nothing about equations. But now, whether two lights will actually intersect or not will be dictated by the particular curvature of space-time, the particular solution to Einstein's equations that will tell you where the light rays travel, etc. They travel as straight as they can. So geometry. So where they intersect, how that will be governed by the Einstein equations, right? So they will tell you. Now, the second intelligence, focusing on light rays. So recall that in Newton's theory, masses which are positive attract each other gravitationally. In general relativity, the analog of this, the curvature of space-time geometry, which is created through the Einstein equations by positive energy matter is such that trajectories of particles and light rays are always focused towards. That is, so in other words, if two particles are traveling, they encounter a mass, they are brought, so that is why they are attracted. Light is also brought together, it's focused. Not only this, but if their trajectories are initially converging each other, right? So supposing I have two particles and their trajectories initially are they're nearby, infinitesimally nearby, and I look at them and they look as though they're converging. And supposing all the matter which you have in your universe is positive energy, right? Then it turns out that this positive energy thing will these trajectories, and in a finite time, these trajectories will necessarily intersect. Okay, and this is true of particles. That was shown by this amazing other person, Madhavan. Another story which I don't have time, but you can look at it. Just a beautiful documentary on Amal Chaudhary, and then people who are from West Bengal, maybe they have heard about him. He's a legendary figure. Now, what Amal Rai Chaudhary showed was he showed that this result for particle trajectories. But I think Sachs and Penrose was just amazing. I think he just proved it for life. Right? But in honor of Roy Chaudhary, even the result that positive energy is light rays and that they come and intersect if they initially converge, that result is governed by an equation which is called the Roy-Chaudhary equation. So even for light, it is called the Roy-Chaudhary. That thing which tells you that there is focusing of light, focusing of particles is what, focusing of light is what was discovered probably by other people, but it is in honor of it called Roy-Chaudhary. Now we put things together, you can see something very, very strange happens, right? So Penrose didn't know about Roy-Chaudhary's result. It's not clear whether he knew about it. What is amazing inside, he derived this focusing. So if you have things which are converging, then and positive energy matter, as we all believe, then things will intersect. Okay. He applied it to a trapped surface. Now, what happens in a trapped surface? Remember the surface? All light rays, the outgoing ones, all of them are initially converging. Right? That is what a trapped surface is. You go infinitesimal neighborhood, outward, all are converging. Therefore, through the Roy-Chaudhary equation, within time, all of these light rays will develop caustics, will all intersect, right? And they will all develop caustics. Already know that whenever you have a caustic, the intersecting light is the boundary of the future. Okay? Therefore, the boundary of the future of a closed surface is finite. Right? Because in finite time, they are going to intersect, leave. So look like, and it looks like something totally crazy, right? This is what would happen in our normal flat space-time. You have a sphere, shine light, and I've drawn a little light cone over here. You have the outgoing rays, right? You have a sphere, you have the, they go on forever and ever and ever, way into the future with expanding. You have the inward ones, and they of course all converge, right? And so they come to a point, and these guys will all exit. They are no longer part of the boundary of the future. So the boundary of the future has this structure, all these dots, and then these things, these endlessly diverging ones. What happens in a trap surface? You see, in a trap surface, the outward guys are also converging. I've drawn it for a particular case where all of them converge to the same point, but that doesn't matter. The inward ones also, light cone structure is tipped locally, right? So local, and then Roy Chaudhary tells you that it will have to intersect, caustics will happen. So remember, this is the boundary of the future of your trap surface. So wherever you shoot your signals which travel less than the velocity of light, they only occupy a finite volume of space-time. They just, so something weird is happening, right? They have to, I mean, presumably they have to end. I mean, they can't escape, they can't penetrate outside because it's a boundary. So you cannot penetrate this part. Everything is within the red and the blue, right? So trap surface, and you look at the boundary of its future, it is a compact set, and that is totally weird. And already you can see that means perhaps it's not so implausible that things are just going to end their life over there, because they cannot continue forever, right? So they just end. That is the simplest possibility, and indeed that is what happens. So one can put in another layer of another few assumptions, and you can, that's what Penrose showed, that in that future, in that region between the red and the blue, you will always have a singularity. And curiously enough, his definition of singularity is a place where these particle trajectories, at least one particle, I think it is light, at least one light ray ends in finite time. Okay. That there was, in all this, there is one light ray which will just end its end. And it doesn't say where it ends is a place of infinite curvature. That is not part, but it will end, and that is, so these are called incomplete geodesics. And whenever you have incomplete geodesics, you say that is the definition of Penrose. Has now shown, due to this completely out of the box idea, that singularities are ubiquitous in the sense that whenever, okay, you have to have a trap surface, right? But people just, you see what people are mucking around with Einstein equations, and suddenly they come with a completely different idea. Just completely different, which doesn't rely on symmetry, it hardly relies on Einstein's equations. And here is right. And so to summarize, Penrose showed that if a trap surface formed anywhere in space-time, a closed trap surface, a singularity would, a closed space-like trap surface, a singularity would definitely form to its. And importantly, if cosmic censorship holds, this singularity would be hidden behind an event horizon, the formation of the black. So he short-circuited the notions. He said there is a sphere, which is questionable, but this is what he believes. Penrose's proof of did not use any symmetry arguments. Trap surfaces are there, that you perturb them away. There's no spherical symmetry. They're pretty robust. So trap surfaces are much more robust objects than finely tuned exactly spherical. Penrose's singularity theorem shook the GR and convinced people finally of ubiquity of singularities in GR. people finally started to believe that black holes could actually be formed in astrophysical collapse. So what is the lesson from all this? And as you all would guess what the lesson is that walking is research. So remember that PC Vaidya was walking up and down, up and down, up and down, and that idea. This is an excerpt from a Nobel Prize interview from Penrose. So lovely. I'd like to read it out. At that time, I was at Berkeley College, somewhere in England, and a friend of mine, also an relativist, Benson, who's an Englishman, but he was working in Dallas, Texas at the time, and I forget what it was. He had a wonderful way with words. So he was talking to me, and we got to this cross. And as we crossed the road, he stopped talking because we were watching out for traffic. We got to the other side, and then he again started talking. And then he left. He went home, and Penrose also went homewards. Then I had this strange feeling of elation, of joy. And I couldn't quite feeling like that. So I went through all the things that had happened to me during the day. I had for breakfast and goodness knows what. And finally it came to this point when I see, and I realized that I had a certain idea, and that this idea was the crucial characterization of when a collapse had reached a point of no return without assuming symmetry or anything like that. So this is what I called it. And this was the key thing. And just like Vaidya went back and wrote down his solution, so I went back to my office and I sketched out a proof. The paper I wrote was not that long afterwards. We took physical review letters and it was published in 1965. I think if I had ever published a Nobel Prize winning paper, I would jolly well remember the year in which I published. I mean, these are all these legendary figures. And Roy Chaudhary is another amazing. I urge you to maybe, the documentary is free and it's available too. And it's really a lovely watch. Him and PC very, very inspiring things. So apart from this, actually Penrose brought about a revolution in the way people thought about. His whole accent was different from just looking at Einstein equations, solving PD. It was more about what events caused what other events, where light trajectories, all that. So his reliance on causal structure, light trajectories, topological arguments, as opposed to an exclusive focus on solving the Einstein. Penrose 3-page 1965 PRL brought him a share of the Nobel Prize. It is often accorded the status of the first magnificent advance in thinking about GR after Einstein's 1953. Because it just opened a new window, right? Some new, completely new way of thinking about it. And another key was introduced was that of Penrose diagrams, which I think probably all too tired, but we can do it later. Just a note, AKR Amal Chaudhary faced immense problems actually working on GR. So he was in, I think he was in cultivation of science, and he had a terrible, I think Sahab made him work in experiments. He was terrible at experiments. He hated it. And I forget the story, but at some point he started teaching in Ashutosh College, and he went back to do his PhD. He was very he started working with N.R. Sen, who was a relativist for there in Calcutta. He thought the guy was not adventurous enough. And then he wrote down these beautiful papers. One on the Roy Choudhury equation, another on really understand, I think, the Oppenheimer-Schneider collapse. Like that. So amazing, absolutely amazing. Now the reason, so these problems, Vishati says, some advisors are terrible, all these problems you can see were there in those years also. Luckily for him, the same John Wheeler who I talked about, he was on the external committee. And Wheeler was an inspirational figure, fascinated by GR. So, in short, that Roy Choudhury's work was well known. And of course, Wheeler himself He's in Princeton. He had a group of exceptional students on their own paths to great discoveries. One of them was Jacob Bekenstein, who we talked about yesterday. And of course, what happens? So, probably I should conclude here because it's been a very long day, and I don't think then there is Hawking as well. But maybe we save that for another day because I think you're tired. Let me conclude. Even as late as the early 90s, when I was doing my 88, people were not really convinced that black holes existed as real astrophysical objects. There was still skepticism. But now black holes are everywhere. And the evidence for the existence keeps piling up. The strongest evidence is from the detection, in my view, of gravitational waves. So what happens in LIGO is that if you look at raw signal which is coming to you, it is actually buried beneath the noise. So what you have to do is cross-correlate that signal with templates. It's called template matching, and then you get a good cross-correlation to come above the noise. But those templates are one of my colleagues in Bala Iyer, he did tremendous, amazing seminal work in doing analytic calculations in what is called the post about what would the gravitational radiation be from a pair of inspiring. And then later on, that served as a beginning for numerical relativity and so on. So because the templates themselves are due to inspiraling black holes, and those are the ones which match the signal, and that's how you signal. In my view, that is what constitutes the biggest evidence that these are inspiraling black holes which are causing gravity wave burst, which what about quantum behavior? This is something which I didn't come to. That is, Hawking showed that while black holes, classically nothing can a black hole, but quantum mechanically, Bekenstein argued that a black hole was entropy. So it was like a thermodynamic object. And then there were some further arguments due to Hawking, which said that it looks like there is also not only the second law, but the first law of black hole thermodynamics. And if you naively believe that, then black holes will have a temperature. And actually, Bekenstein got very depressed when Hawking found this result. And it was just an analog. There was something in this whole business where it looked like classical something where you could formulate some behavior of black holes which looked analogous to the first law, and there was some term over there which looked like this. That was it. More profound. But Bekenstein took it too hard, and he just didn't know what was going on. He said, how can I radiate and so on? And then miracle happened, and Hawking in the early 70s showed that while classically quantum mechanically it can radiate at what is called the Hawking temperature, and then puzzle about information loss that we don't have time to get into. Indeed, whether these speculations about quantum behavior and the endpoint of evaporation and actually transform into reality, just as astrophysical black holes actually did, objects, or not, the puzzle of black hole entropy, which unfortunately I didn't have time. I told you about what could be the microstates which will conflict for black hole entropy, and the information loss problem challenge the imagination, invite curiosity, and perhaps serve as rare theoretical clues. So thanks a lot, and I hope